In exercise 2C, we start to look at the algebraic derivation of the derivative of the exponential function. So you saw the graphic representation of the derivative, and you could see that there was a number somewhere between 2.718, around 2.718, in which that if you raised that to the x power and kept varying x, you took that graph and you calculated the gradients at various places along there, the equivalent of finding its derivative, the value of the gradient, different places, then you get exactly the same function. So you know that graphically you could see that the graph of the derivative was exactly the same as the original function, hence we would say that the derivative is also e to the power x. All that's going to happen here now is we're going to show it algebraically. To do that, you need to use this definition. Now, you don't need to know this definition of e to the x, but e to the x can be defined as 1 plus x squared on 2 times 1 plus x cubed on 3 times 2 times 1, x to the 4th on 4 times 3 times 2 times 1 plus ... And by the way, this 4 times 3 times 2 times 1, that's called 4 factorial, 3 factorial. You'll remember this from the preliminary course, 2 factorial. Now, and just out of interest, so e to the power 1 will be 1 plus 1 plus 1 over 2 times 1, which is a half, plus, because x, remember, was 1. We're trying to show that e is actually this number 2.7, that we actually know it is. So put 1 in here, and we'll get 1 on 6. Put 1 in here, 4 3s are 12, 2s are 24, 1 on 24. Should we add these up, or find the limit, as x approaches infinity of that, you do get the number 2.7 ... So now that's not showing anything about the derivative, that's just showing the definition of e to the x and actually what e to the 1 would be. So we're going to go back to here and we're going to differentiate this expression here with respect to x. So take the derivative of e to the x is like taking the derivative of this side as well. So 1 would go to nothing. Derivative of x goes to 1. So the derivative goes to 1. The derivative of this term, bring the 2 to the front, subtract 1 from the index, differentiating, and you'll find your 2's cancel out and you just get x to the power 1. Then for this one, bring 3 to the front and you'll have x squared, and then the 3 will cancel and you'll just have x squared over 2. Bring the 4 to the front, the 4's will cancel and we'll have x cubed, subtract 1 from the power, x cubed over 3 times 2, x cubed over 3 times 2. If you could imagine the next term, you bring 5 to the front, it would be over 5 times 4 times 3 times 2 times 1. The 5's would cancel out, the power's back to 4, and we would have this x to the 4th over 4 factorial. But if we stop and look at this expression, it is exactly this. It's 1 plus x squared on 2, x squared on 3 factorial, x to the 4th on 4 factorial, etc. And we know we define that as e to the x. So we then can say that d dx of e to the x is e to the x. And that just supports that's an algebraic derivative of the exponential, and you saw a graphical representation of the derivative of, we hadn't identified it at that stage as e, of this number 2.718, etc. So now that we've got our derivative, and this is really important, so this is basically the second rule that we have for derivatives. So you can see it's not bring the power to the front and subtract 1 from the power. No, that is definitely not how you differentiate e to the x. We did not bring the x to the front, and we didn't certainly have subtract. So totally different rule. Only can be used when you've got e to the x as a function in x. Only for this exponential. So it's not even what we would do for 2 to the x. It's only can be used, this pattern, for e to the x. Make sure we really understand that. However, some things do stay the same. The function of a function rule has to be followed. So when we've got t to the x of e to the something going on here with the x, so e to a little function in x. So e to this is our original function, and then within that there's something going on. So e to the ax plus b would differentiate to give e to the ax plus b, following this. It doesn't matter that it's a little bit complicated there, we keep all that complication. However, then we must differentiate that. Now, to differentiate that will require our very first rule, where we bring the power to the front, and we subtract 1 from the power and differentiate a constant that goes to 0. So you can see that we end up with an a, and sometimes you'll see me do them where I write it as e to the ax plus b times now the derivative, which is a. And then we know for most expressions, and this is an expression, we would take a constant, a is a constant, we would take that to the front. So that's all that's happened between there and there. This is in more generalised form. E to the function in x, then if y is that, then y dash, differentiating with respect to x, is, you'll see me write it as e to the function in x times f dash x. And then I will take this and put it at the front. So that's what's actually happened underneath. So that f dash x just got taken, placed at the front, times the original function. So that rule still applies and must be followed. And you saw that back with your previous rule for differentiating. The product rule remains. So anytime you've got a product of functions, and obviously one of these functions is going to be an e to the x, you must follow the product rule. So what was the product rule? Take the first function, multiply by the derivative of the second, plus the second function times the derivative of the first, where you can now expect one of these functions to involve an e to the x. And then it probably nicely follows that if the product rule must be obeyed, then the quotient rule must be obeyed. And so we'll have that if you've got y is equal to, remember it's v over u. So function in x over a different function in x, then we will use, it's u on v. We take v, the function from the bottom, and multiply it by the derivative of the top function. Now we're going to be subtracting more than one thing. I strongly recommend you put that in brackets all over your v squared. Now this is on the formula sheet. This was something that the markers noted that students were not using. They were being like me and they were getting it wrong. Don't let that be you. Use the formula sheet and get the correct functions in the right spot. I will stop the video there and I will do these examples in another video.